eigenvectors, right? And the eigenvalue and eigenvector play some important role in the linear algebra. And actually, this is the starting point of the matrix decomposition. So as I mentioned a little bit in the last lecture, so matrix decomposition is very, very important. So what is matrix decomposition? So we just decompose a matrix A into the multiplication of several simple matrices. Like what type of simple matrix? For example, triangular matrix, diagonal matrix, orthogonal matrix. So maybe some of those names you are not so familiar with, but some of those you already know, like diagonal matrix, right? Triangular matrix. Orthogonal matrix is a matrix that whose if P is an orthogonal matrix, then P transpose times P equal to identity. So it's a very special matrix, right? In terms of multiplication, it's very special. So if we decompose a general matrix into some special matrix, so some operations will be simplified. For example, in real application, we also mention a little bit later in an example that many times we want to calculate the a power k, and we want to calculate when k goes to infinity, what's the value of a power k. For general matrix A, it's impossible for us to do any calculation like this, right? But we know that for a diagonal matrix, we know how to compute each diagonal element power k, right? That's the A power k. Does that make sense? If A is a diagonal matrix. So things would be much more simplified. That's why we need to do the matrix decomposition. So, okay, eigenvalue, eigenvectors is related with the matrix decomposition. Okay, so first thing first, what is eigenvalue? What is eigenvector? So for a special matrix A, A is n by n matrix. There exists some special vectors, such that this vector under the linear transformation A times x, the vector x actually don't change too much, right? So it's still lying on the same line, and with a scalar lambda. So that's why we call lambda the eigenvalues of A and x is called an eigenvector corresponding to lambda. Make sure here is lambda x, they appear simultaneously. That's why we call lambda eigenvalue, but x is called eigenvector corresponding to lambda. And so how to find those eigenvectors? So for eigenvectors, we know that if we are given eigenvalue, so for eigenvectors, so x satisfies Ax equal to lambda I, right? So which is actually equivalent to solve A minus lambda I times x equal to 0. So we find the non-zero solutions for the homogeneous equation A minus lambda I times x equal to 0. So lambda, then what's the condition for lambda? Lambda means that for the equation A minus lambda I times x equal to 0 has non-trivial solution, which means the determinant A minus lambda I equal to 0, right? So that's why here we call the characteristic equation A is n by n matrix, then the determinant A minus lambda I equal to 0 is called the characteristic equation of A. And this, the left-hand side actually is a polynomial. So we call determinant A minus lambda I is called the characteristic polynomial of A, a polynomial of degree n in the variable lambda. Okay. Now, as I mentioned, so how to find eigenvalue? We just find the solution for the characteristic equation determinant A minus lambda I equal to 0. Okay. So now let's review the determinant. So look, calculating this determinant A minus lambda I, it's not so trivial. Remember, calculating the determinant is not trivial. If A is a 2 by 2 matrix, it's much easier to solve this characteristic equation. But what if like it's 3 by 3, 4 by 4 matrix? Solving it involving too much calculations. So here we are review some important results we learned so far for the determinant. So in order to calculate the determinant, we know that we can do the row operation, right? Scaling, interchange, replacement. And the value of determinant will change as well, but the change is not so much, and we can change it back, right? So especially like the interchange, we only need to add a negative in front of it. Replacement won't change the value of the determinant. And the scaling, we scale it back, right? And we know that in order to change a matrix A into the echelon form, so scaling is not necessary. In order to get reduced echelon form, because we need to make every element in the pivot position to be 1, so we have to use the scaling. But in order to make it to be the echelon form, we don't have to do the scaling. That makes sense? So that's why here, if we we say A is an n by n matrix, U is an echelon form of A by row replacement and row interchange without scaling. Because scaling will change things, change the determinant a lot, right? So we need to know how much scaling we use. So in this result, we don't use scaling. Then the determinant of A is just equal to the determinant of U subject to some psi value. And the psi value is -1 power R. What is R? R is how many times you use interchange. If I use twice, then this value is positive, just equal to 1, right? So if U is not invertible, which means that the determinant of U equal to 0, so determinant of A equal to 0 too. If U is invertible because U is already the triangular matrix, the determinant for the triangular matrix is the product of the diagonals, right? So in general, we know how to calculate a determinant. Okay, now let's see a theorem. If A is an n by n matrix, then A is invertible if and only if we know that if invertible, the determinant of A is not 0. And what is the number 0 is not an eigenvalue of A? Look, if lambda 0 equal to 0 is an eigenvalue of A, which means determinant A minus lambda I equal to 0, right? Lambda equal to 0, what is that? It means determinant A equal to 0. Determinant A is equal to 0, so A is not invertible. That's why lambda equal to 0 is not an eigenvalue here. That makes sense? So these two conditions are equivalent to each other. Okay? So here, there are 3 conditions. A is invertible, lambda equal to 0 is not an eigenvalue, determinant A is not equal to 0. So these 3 conditions are equivalent to each other. So as long as we are given one condition, then the other conditions are true. Clear? So next, let's see another result. Properties of the determinants. So this is the thing we already learned before. A is invertible if and only if determinant of A not equal to 0. Also, we have learned determinant A times B equal to determinant A times determinant B. But here you need to make sure that both A and B are square matrix. Determinant H transpose equal to determinant of A. If A is triangular, so triangular is like this. Here, this matrix is up triangular matrix because the up portion is non-zero. But you can also write triangular matrix including up triangular or lower triangular. Okay, here I only write down one case, up triangular. But you can lower triangular means that the upper portion is element is zero, down portion is non-zero. Okay. So then the determinant of A is just the product of those diagonal elements. A low replacement operation of A then changes the determinant. A low interchange changes the sign of the determinant. A low scaling also scales the determinant by the same scale factor. Those results we have learned before, right? Now, let's to solve this problem. Let A be this matrix, find the characteristic equation of A, find all the eigenvalues of A. Could you go ahead and solve it? Because this matrix is very simple. It's an up triangular matrix, right? So what is the characteristic equation of A? And find all the eigenvalues of A. So this, right? And this one equal to the product of the diagonals, because this is still an up triangular matrix. So the determinant of A minus lambda equal to 5 minus lambda, but here we have 2 5 minus lambda, so it's square, 3 minus lambda, and 1 minus. So 2, this is a characteristic equation, is equal to 0. And for problem 2, because we just need to solve this equation, let determinant A minus lambda I equal to 0, we have minus lambda square, 3 minus lambda times 1 minus lambda equal to 0. So lambda 1 equal to lambda 2 equal to 5, lambda 3 equal to 3, lambda 4 equal to 1. Now let's see, the characteristic polynomial of a 6 by 6 matrix is this formula, find eigenvalues and their multiplicities. Do you know what's the meaning of multiplicity? Multiplicity is that the root, like a 5, how many times it appear? So there appear 2, right? So for this value, so their multiplicity is 2. Here, because this root appear only once, so the multiplicity is 1, 1. Clear? So for this equation, we can do it together. It's very simple. So lambda power 6 minus 4 lambda power 5 minus 12 lambda power 4 equal to lambda power 4 here, lambda square minus 4 lambda minus 12. So which is equal to lambda power 4 here is lambda minus 6 times lambda power 2. So eigenvalues, lambda equal to 0, lambda equal to 6, lambda equal to -2. Here be careful that lambda plus 2, so the root is lambda minus 2. The reason is very simple, so because we need to make this equal to 0, so which is lambda equal to -2, right? So it's not 2. So because this is the type of mistakes some students make in exams as well, so I want to mention a little bit here. So in terms of multiplicity, lambda equals 0, so look, multiplicity is determined by the power here. So here is 4. For this one, multiplicity, there's no here, which means here is power 1, right? So that's why it's 1. For this one, multiplicity is power -2. Okay. Now let's see another exercise problem. Find the characteristic polynomial and eigenvalues of the matrices. Okay, so we can do it together. For the first one, look, this matrix is more general than the one we encountered earlier, right? So look at the first one. So characteristic polynomial is determinant a minus lambda I, right? Lambda I is all the identities, the diagonal matrix with all the diagonal to be lambda. So this determinant, which is equal to 5 minus lambda, -2, 3, 0, 1 minus lambda, 0, 6, 7, -2. Is that correct? So look how to simplify it. Look, you may notice this row is that all 0 except the diagonal, right? So you can expand according to this row using the cofactors. So then here, which is equal to 1 minus lambda, but don't forget it's -1. What's the power? 1 minus lambda, second row, second column, right? So it's 2 plus 2. Although in this example, if you forget, it doesn't matter too much because it's positive. But what if it's a negative value? So always remember to add the factor. Then this cofactor, right? Then the remaining is that you delete the corresponding row, corresponding column. So what we get is 5 minus lambda, 3, 6, -2 minus lambda. So which is equal to 1 minus lambda. Here is 5 minus lambda times -2 minus lambda minus 18. So which is equal to 1 minus lambda. Here is -10. We multiply it out. Here is minus, here is plus 2 lambda minus 5 lambda plus lambda squared minus 18. Right? We do the multiplication like 5 times -2 is -10. 5 times negative lambda is -5 lambda. negative lambda times negative 2 is true lambda. Negative lambda times negative lambda is lambda squared. So this is equal to 1 minus lambda. Here is lambda squared minus 3 lambda minus 28. What's that? This is equal to 1 minus lambda times lambda minus 7 times lambda plus 4. So how to do this factorization? Look, check the coefficient of lambda square and the constant. Okay, so we do the factorization. 1, we can factorize 1, 1, right? Negative 24, so you have just many factorization, like 4, negative 7, negative 7, 4, and 1, negative 8, negative 1, 28, like this, right? There are many factorization. Then which one should we choose? Here, the constant negative 3. So if we put negative 7, 4, then what's the calculation here? You do the multiplication, 1, 4. Diagonals, 1, 0. Then add them together, we get negative 3. This negative 3 should be consistent with this number here. Okay? Then what's those numbers? 1 is here. Negative 7 is here. So it's 1 factor. And 1, 4, 1, 4. Clear? So we do this type of factorization. And then you get the solution. So let this equal to 0. You get lambda 1 equal 1, lambda 2 equals 7, and lambda 3 equal to negative 4. Okay. So now there's another method I want to mention a little bit. So everyone knows that one solution lambda equal to 1. So some students still have difficulty to factorize this. Then I can tell you one formula. A lambda squared plus E lambda plus C equal to 0. We have a formula for lambda equal to root formula, here, quadratic formula, 2a, negative b, positive, for b squared minus 4ac. This is lambda 1. Lambda 2 is 2a, negative b, minus square b squared minus 4ac. Okay? So you can use this formula if you don't know how to do the factorization. So the eigenvalues are here, so this problem is solved. Now let's go ahead to solve this one. Could you try first, then we solve it together? So A minus lambda I, because the diagonal is all zeros, so the diagonal become all negative lambda, right? 0 minus lambda. So all diagonals negative lambda, and then all other elements of A is keep unchanged. So then some students stuck here. How to proceed? Look, if you put the negative lambda here in the pivot position, obviously it's not a good choice in order to make the underneath element to be 0, right? Because then you need to do the scaling like 1 over lambda. Is this doable? We are not sure. What if the solution have lambda equal to 0, right? So, in this case, for the first column, you just choose the simplest non-zero element. So, in this column, here we have 3 elements, negative lambda, 3, 1. Which one should we choose? 1, right? So, that's why we interchange the first row and the last row. That makes sense? So we interchange the first row and the last row. When we do the interchange, we need to add negative in front of it to make it still equal to the original determinant. One, 2, negative lambda. Now we can make those elements to be 0 by doing the replacement. So one replace that I can do is that row 2 minus 3 row 1. We get new row 2. Because the replacement won't change the value of the determinant. So we can do directly. So this is 0. Negative lambda minus 6. 3 plus 3 lambda. And then the last row, row 3 plus lambda times row 1, get the new row 3. So this is 0. 2 plus 2 lambda. 1 minus lambda squared. Then you can see that these columns only one non-zero, so we get negative. Here is negative lambda minus 6, 3 plus 3 lambda, 2 plus 2 lambda, 1 minus lambda squared. So this is equal to negative. Here is negative lambda minus 6 times 1 minus lambda squared minus 3 plus 3 lambda times 2 plus 2 lambda. Okay, we got this one. Then, how to proceed? Can we expand it directly or doing something else? Look, if we expand directly, you can see these two polynomials are all of degree 3, right? So factorizing a polynomial of degree 3 is not so simple. So first thing first, we would like to check these two polynomials separately. Do they have a common factor first? So do they have a common factor? Yes, right? The first term contains 1 plus lambda, right? And the next term also 1 plus lambda. We can factorize it out. That makes sense? So if you factorize 1 factor and then the remaining is only a quadratic equation, it's much easier to solve. Even you don't know how to factorize it, you can use the quadratic formula to find the solution directly. So this is lambda plus 6, lambda minus 1, lambda plus 1. Okay, so here, and I do first thing first, and here is minus negative. So this becomes lambda plus 6 times lambda square minus 1. And then I do the factorization, we get this one, okay? And then the next term is minus 3. Here is lambda plus 1 times 2 times lambda plus 1, right? So we factorize it out, is negative lambda plus 1. Here is lambda plus 6 times lambda minus 1 minus 6 times lambda plus 1. So now there's no common factor, so we can only do the simplification. We multiply it out, so this is lambda squared plus 6 lambda minus minus 6 minus 6 lambda minus 6. So which is negative lambda plus 1 times lambda squared minus lambda minus 12. So as I mentioned, how to factorize this one? Look, it's 1, 1, negative 4, 3, right? So which is negative 4 plus 3 equal to negative 1. So that's why we have this factorization here, lambda minus 4, lambda plus 3. So we have solution, lambda 1 equal negative 1, lambda 2 equal 4, lambda 3 equal to negative 3. So these are the eigenvalues. Clear? So our question is that find the characteristic polynomial and eigenvalues. So polynomial here is this one. Eigenvalues is this one. Okay? So but in exams you need to write down the conclusion, okay? In wording. So you need to write down. So the characteristic equation, the polynomial is this one, and the eigenvalues are this one. You need to write down clearly. Yeah? Okay, so this is how to calculate the characteristic polynomial and the eigenvalues for 3 by 3 matrix. Do you have some ideas by now? Do you have? Right? So first check this determinant. If you can expand directly, if there's involving a lot of zeros, so you do the better do the expansion directly, right? If not, you first column you find the simplest element and do the interchange first before you do the replacement. That's the general way we do the calculation for this type of problem. Now let's see another important concept, similarity. So this is one type of actual matrix decomposition. So we can see that two matrices, A and B, are similar to each other if there exists an invertible matrix such that P inverse AP equal to B. So here we don't have any restriction on the matrix A. But look, if A is a diagonal matrix, you can see that it could be viewed as a decomposition for matrix B, right? Be decomposed as an invertible matrix times the diagonals, right? Times, so P inverse AP here. But the concept of similarity, we don't have any constraint on the matrix A or matrix B. But we only say if there exists an invertible matrix P such that P inverse AP equal to B. Or equivalent A equal to PB, P inverse, it doesn't matter, okay? So changing A into P inverse AP is called a similarity transformation. Now, let's see a very important theorem. If n by n matrices A and B are similar, then they have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. If n by n matrices are similar, then we have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. How to prove? Polynomial characteristic, so you just calculate determinant a minus lambda I, right? That's for sure, right? And then you calculate determinant b minus lambda I. But we need to use the relationship between a and b. A equals P inverse B A, right? The proof is actually it's simple if you figure out the relationship between these two. Look. Proof, because they are similar, so if A and B are similar, then here is this an invertible matrix P such that by consider with P equal P inverse AP. Is that clear? So hence, B minus lambda I, because eventually I need to calculate determine B minus lambda I. So I simplify first. I want to relate it is with the matrix A. Then what's that? This is exactly P inverse AP minus P inverse lambda I times P, right? So this is an important one, because if I do, because eventually I want to connect this with A minus lambda I, right? So how can I get A minus lambda I? We have A here, but the lambda I here, but here we have P inverse P. Remember, P inverse P equal to identity. So that's why here is also identity, so I can add P inverse P here. So by doing so, it's a good improvement. Look, it's just like this. That's a good part, because if we have this formula, then determinant B minus lambda I equal to the determinant P inverse A lambda I, A minus lambda I T. Remember the property of the determinant. So here is determinant P inverse times the determinant A minus lambda I times the determinant P. Do you know how to solve now? Look, here is, you can move these two together, right? Actually, we already, if you remember this result, then the problem is solved. Remember, we have this result. Do you remember this result? Right? But if you don't remember, it doesn't matter as well. You can use this one, A minus lambda I, determinant P inverse times the determinant P. Look, here is equal to determinant A minus lambda I. Here is determinant P inverse times P. Right? That make sense? So this is exactly is one. Identity, right? So this is equal to determinant A minus lambda I. So this proves that determinant B minus lambda I equal to determinant A minus lambda I. So they have to share the same determinant. contains the same characteristic polynomials. So that's why they have the same eigenvalues, right? The same equation leads to the same root for sure. So the magic here is this one. Is this one, okay? This portion. That's the key portion. And then with this, then we get this one, and this one you get this. So this technique is very special, and you are required to grasp this technique, okay? So maybe it will appear in exam in some other ways. Not like I ask you to prove something, but maybe in some other ways. So here, this one side want to emphasize that if two matrices they share the same eigenvalues, are they similar to each other? If two matrices and they have the same eigenvalue, are they similar to each other? Are they similar to each other? Do you know? We know that two matrices, if they are similar to each other, then they share the same eigenvalue, right? What if the opposite? If two matrices share the same eigenvalues, do they have the same? Do they similar to each other? Similar. Same eigenvalue? Same eigenvalue? Are they similar? If not, can you give me a counterexample? So what's the answer? Can you guess? True or false? Same eigenvalue, two matrices are similar. If A and B share the same eigenvalue, then A is similar to B. Is it true or false? True or false? False. Okay? It's not correct. I can give you a counter example. It's very easy to construct. Remember that the triangular matrix, right? The determinant is exactly the product of diagonal. But what if the diagonal matrix, the determinant also the product of diagonal, right? So you just create two matrices. One is triangular, one is diagonal. Look, these two matrices, they are not similar, even though they have the same eigenvalues. They are not similar to each other, for sure. Okay, so also similarity is not the same as row equivalence. So row operations on a matrix usually change its eigenvalues. Some of you may think that in calculating the determinant we do row operation, yes, but the determinant is already the matrix A minus lambda I, not the original matrix A. That's the difference. That makes sense? So if A and B are row equivalent to each other, then their eigenvalue may not be the same. Clear? So when we do row operation for the determinant, for the polynomial characteristic equation, we are calculating A minus lambda I, or we are already doing this, right? But A is equivalent to B, we only do the row operation on matrix A. So these are two different concepts. That make sense? Okay, next. Now we see a new application. So in this example, I just want to show just want to let you know that it's a common question that we need to calculate a to power k. Okay. So look at this example here. We don't give you any physical interpretation of this problem. So actually, this problem could be like that. I remember there's a problem like owls eat mouse, and then so we can represent that the population of the owls and the population of the mouse, and then we know that owls will eat the mouse, and also they also have their own like birth rate, right? So actually, this system can be represented by this equation. Like xk maybe can represent that xk when the first element represents the population of the owls, and next element can be represents the population of the mouse, right? At time k, for example, like the case state, for example, or the case mouse. Does it make sense? So many dynamical systems can be simplified to use this model. These are very simplest dynamical system. So what is dynamical system? It's a system that the value changes with time t. Does that make sense? So right now, because this is a math course, so we forget about the modeling portion. So I just give you that this model is come from the real application. Xk is a vector, then each element actually represents something, right? And this vector changes with time, and the relation is how it changes. It can be modeled by sk plus 1 equal to axk, with the initial value x0 equals 0.6, 0.4. Okay, so my question is, what's the long-term behavior? Long-term behavior, which means that what's the value of x? xk when k go to infinity, something like that, right? That makes sense? So how to calculate this value? Look. So what we need to do is that I do the analysis. So here you can see x1 equal to ax0, right? x2 equal to ax1, which is equal to a times ax0, a squared x0. x3 equal to ax2, equal a times ax2, a squared x0, a cubed x0. That make sense? So in general, here is xn equal to an x0. So, or in general, if we use k, so here, if you want to analyze the long-term behavior, what we need to do is that what's the limit as k go to infinity? That's the problem I'm thinking. So look, a to power k here. So that's why we need to calculate a to power k. How can we calculate a to power k? That's almost impossible for us right now, right? Here, we need to use the matrix decomposition, but the matrix decomposition still looks not so I mean, you may not so familiar with. So here, I use the eigenvalue eigenvector. In the future lecture, I will reinterpret it later as the matrix decomposition. They are actually exactly the same, because eigenvalue eigenvector corresponding to that eigen decomposition. Okay, the matrix decomposition. So how to calculate A2 power k? Any ideas? And as I mentioned to you that A2 power k is doable for A is a diagonal matrix, right? Okay, so we don't know, but what if like x0 is the initial value, then nothing we can do. But we know that also another thing you may remember that what if x0 is an eigenvector? Then A2 power k x0 is doable, right? If x0 is an eigenvector, we can compute. That makes sense? But x0 is the initial population. How is it possible that it's an eigenvector? No, there is no possibility. But remember, like A is 2 by 2 matrix. What if it has 2 eigenvectors? Then these 2 eigenvectors are linearly independent. This is correct, right? Linear independent vector in R2 is a basis. If it is a basis, then x0 can be represented as a linear combination of these 2 eigenvectors. So here I just want to illustrate the idea, so why we do it this way. C1, for example, V1, V2. This is 2 eigenvectors, right? Then this is just C1, AKV1, plus C2, AKV2. Look what's happening. If V1 is an eigenvector, so which means that equal lambda 1 V1, right? And V2 is an eigenvector, which is lambda 2 V2. Okay? So then this becomes to be C1 lambda 1k V1 plus C2 lambda 2k V2. The problem almost solved. So what's the question left? We need to calculate V1, V2, lambda 1, lambda 2, C1, C2. If we find those values, then the limit is computable. Does it make sense? So that's the power of eigenvalue eigenvector. Look, we can use it to solve the A2 power k. So that's why in this problem, our first step is calculate the eigenvalue eigenvector for matrix A. Okay, so this is the idea, so I will delete it. This is something you can write down in your draft, so you have some global picture of how to solve this problem. That make sense? If I don't illustrate like this, so you may confuse why at the very beginning I calculate eigenvalue eigenvector. Does that make any sense, right? Now you understand it much better. That make sense? So now I do the details. So keep in mind we need to calculate lambda 1, lambda 2, V1, V2, and so we first, that's why we first find each eigenspace. Determinant 0.95 minus lambda 0.03, 0.05, and 0.97 minus lambda. So now, for this equation, we are not able to do the factorization. So what we can do is that we just use the quadratic formula. Lambda equal to 2a negative b positive negative 1.92 square minus 4 times 0.92. Over 2. So lambda 1 equal 1, lambda 2 equal 0.92. Now we calculate for lambda 1 equal 1. 0.95 minus 1, 0.03. So we find the corresponding eigenvectors. So this is trivial ones, so I just do a little bit fast because this is 2 by 2 matrix, right? So here you can see x1, x2, so here is c times 3 times 5. That's easy, right? So some of you may ask that, we can do like, as I mentioned earlier, we do it like this, 3 over 5 x2. Yeah, you can do this way, but actually it's the same thing. So this is actually is 3 over 5 x2. Here is x2, so this is x2, 3 over 5, 1. But we prefer to use integer, so maybe I can move 5 outside, so it becomes 3, 5. Okay, that makes sense? So this is, I replace it by a scalar c. So now we get, so the eigenvectors is 3, 5. Similarly, for lambda 2 equals 0.92. So I do the same, okay? So then I get solution directly, which is equal to C1 to 1. So V2 equal to 1 to 1. So look, these two vectors are obviously linear independent, right? So it's a basis in R2. So now I return x0 equal to C1 V1 plus C2 V2. So this can be written as V1 V2 C1 C2. So what is C1 C2? How to find C1 C2? We know x0. We know V1 V2. V1 V2 actually this become to be a matrix. This matrix is invertible, right? So actually you just solve this equation and C1 C2 we get the value. C1 C2 is the value we need to count. So this is V1 V2 inverse times, and x0 is, so the result is equal to 0.15, 0.225. Okay, so with those values in mind, then we can calculate the result we mentioned earlier. So look, x1 equal to a x0, which is equal to now C1 AV1, right? Plus C2 AV2. So this is, those numbers is doable. And V1 is lambda 1 equal to 1. So C1 V1 plus C2 0.92 V2. Okay, and then x2 equal to a x1. So which is equal to a C1 V1 plus C2 0.92 V2. So we get C1 V1 again plus C2 0 C square V2. So this actually is lambda 2 square, right? And why there's no, because lambda 1 is equal to 1. 1 per k is always 1, right? So that's why here. So in general here, xk here equal to C1 V1 plus C2 0.92 per k V2. We know that for a scale constant between 0 to 1, then the power of k go to 0 when k go to infinity, right? So the second portion disappears. And just C1 V1. C1 V1 is the value we know. So we know that it goes to the stable state and with a constant value of xk. So this is the solution for the so this go to C1 V1 and k go to infinity. So we solve the problem. Okay. So we finished the lecture today. So actually this lecture is very important. So I provide several actual exercise problems, and we can do a little bit fast. We just give the rough ideas here. Okay. Look at this example. Show that if A equal to Q times R with Q invertible, then A is similar to A1 equal to RQ. So in order to prove two matrices are similar to each other, what we need to find is matrix P, right? Such that A equal P inverse A1, A1 P times P. So then we just compare the two matrices and then how to find the P. Does that make sense? Look, if I write down it more clearly, you may notice what's the difference here. So I want to find P inverse AP, which is equal to P inverse Q RP. I want to equal A1 RQ. I want to equal to RQ. So look, this is almost RQ, right? If I choose, we choose P equal to Q. What happening? This is RQ. And this one, this portion, P inverse Q equal to identity, right? So this P is exists, right? solve the problem. That makes sense? Look at the second one. If A and B are similar, then determine A equal to determine B. A and B are similar, so which means that there exists an invertible matrix P such that A, so we have invertible matrix P such that P inverse AP equal to B. They are determinant equal to each other or not? Yeah, determinant P inverse AP. Determinant of B equal to determinant P inverse AP. So which is equal to determinant P inverse, determinant A, determinant P equal? Right? So this is, as I mentioned, determinant P inverse just equal this. Equal to determinant. Now, next. So, mark each statement true or false. Justify each answer. The determinant A is the product of the diagonal entries of A. Is it true or false? This is only true if A is triangular matrix, right? Here is general, so it's false. You just give a general matrix like 1, 2, -3, 1 like this. This matrix, the determinant of A is not the product of the diagonal entries of A. Right? Elementary row operation of A does not change the determinant. Interchange changes the negative, right? Change the sign. So this is wrong as well. Interchange and scaling will change the determinant, but won't change it too much. That's why we can do row operation. So the last one here, yeah, this is true. Because determinant A, which means it's meaningful, right? Times this. For if lambda plus 5 is a factor of the characteristic polynomial of A, then 5, no, -5, okay? This is I mentioned in the class as well, right? Lambda plus 5 equal to 0, we get lambda equal to -5. Now, let's see this exercise problem. Show that A and A transpose have the same characteristic polynomial. This is easy to prove. Determinant characteristic is A minus lambda I. The characteristic polynomial of A transpose minus lambda I. Are they equal? Yeah. Determinant A equal determinant A transpose. So A transpose minus lambda I transpose. I transpose equal to identity, right? So that's why. Simple? Last. Look at this matrix V1, V2, V3, W. Show that V1, V2, V3 are eigenvectors of A. How to show they are eigenvectors of A? Do you remember? You just check A, V1, right? If this is a scalar of V1, and you just check A, V2 and find another scalar equal to V2. A, V3, calculate if it's still proportional to V3 and find the scalar, right? That's how we check if they are eigenvectors or not. And the answer is yes. And actually, for the first one, is lambda 1 is just 1. For the second one, lambda 2 is equal to 1/2. And the last one is lambda 3 equal to 0.2. So, but you needed to do the calculation to figure it out. It's simple, right? We mentioned it many times before. Now, so V1, V2, V3 are eigenvectors. And then B, let X0 be any vectors in R3 with non-negative entries whose sum is 1. Explain why there are constants C1, C2, C3 such that X0 equal to C1, V1 plus C2, V2 plus C3 by V3. Do you know why? Because V1, V2, V3 are eigenvectors with different eigenvalues, which means they are linearly independent. You remember this result? For the eigenvectors corresponding to distinct eigenvalues, they are linearly independent. Do you remember that theorem? In the last lecture we learned, right? If A has R distinct eigenvalue, lambda 1, lambda 2 to lambda k, their corresponding eigenvectors B1 to Bk are linearly independent. Do you remember that theorem? So here, in the proof A, we show their eigenvectors and with corresponding eigenvalues, you can see is 1, 1 over 2, 0.2, they distinct to each other, right? So they are linearly independent. So the theorem we learned in the last lecture is very important. And R3 is the dimension 3. So we have 3 linear independent vector and they span the whole space, right? So they are the basis. So if they are the basis for any vector in R3, they can be linearly represented by these 3 vectors. So which means there exists C1, C2, C3 such that X0 equal to C1, V1 plus C2, V2 plus C3, V3. Is that clear? And then next is that you reduce that C1 equal to 1. That's simple. Why? Because of the properties of V2, V3, look, V1, V2, V3. Do you see the property here? W. So here I want to mention that W transpose V1. What's the result? This is 1, 1, 1 times 0.3, 0.6, 0.1. Do you know how to calculate this one, right? So this is equal to 0.3 plus 0.6 plus 0.1 equal to 1. But WT times V2 actually equal to 1, 1, 1 times 1, negative 3, 2 equal to 0. Okay? And similarly, WT-V3 equal to 0 as well. So how to get this result? So I multiply both sides by WT. Then what we get is 1 equals C1 plus 0 plus 0. That's why we got C1. Simple? So in today's lecture, we mainly discussed on how to find the eigenvalues through characteristic equation, right? Especially like for 3 by 3 matrix, how to calculate the determinant. That's the key portion. And also we discussed the concept of similar. 2 matrices are similar to each other, right? And also we discussed one application of the eigenvalue eigenvectors for the dynamical system. So how k goes to infinity using eigenvalue eigenvector, we are able to calculate it. And in the future lecture, I will also use another way to do it, to find the result for the dynamical system. Okay? So we use the matrix decomposition. So we just understand the same stuff in another terminology. That's it. In another notations. Okay? So that's all for today's lecture.